Good afternoon and welcome to the Open Systems Media webcast, The Current State of Machine Vision Technology. My name is Rich Nass and I am the Executive Vice President of Open Systems Media. I lead the embedded and IoT teams for embedded computing design, but more importantly, I will be your moderator for this webcast. This afternoon, you'll be hearing from one of the industry's experts in machine vision. That would be John Gerard. He is a Senior Director with the Intelligent Sensors Group at ON Semiconductor. Just a bit about John. He has more than 20 years of experience in the CMOS imager and video semiconductor business. He's worked 10 years in semiconductor design and video systems engineering, and he holds a Bachelor's of Science in Electrical Engineering from UC San Diego and Executive MBA from UC Irvine. So before I bring John out, let me just say two words about the topic today and what you can expect to learn from this webcast. You're likely aware of all the buzz that's around artificial intelligence and machine learning. If you're not, you haven't been paying close attention. There's a good chance that you're already working on a design that has this integrated into it, and if not, it'll likely be in one of your upcoming designs. To that end, one of the significant portions of AI and machine learning is machine vision, and that will likely take on a significant role within that design. It's difficult to imagine an AI system that doesn't involve some aspect of machine vision. So that's what you'll be learning on this webcast, and I know that I am looking forward to it. First, let me go over some of the housekeeping stuff. The entire presentation will likely take around 45 minutes, give or take 5 minutes, and that'll leave us plenty of time to answer your questions, and we'll get to as many as time permits. You'll find on your console window an area where you can enter your questions in real time. And as I said, we will address as many as we can when John is done. If we don't get a chance to answer your question, someone from ON Semi will get back to you after the webcast is over. So every question will be answered. If you have a question that pertains to the webcast operation, like the problem with the slides or the audio or something like that, put that question into the console and one of the technicians will respond to you with a solution. There's also a maximize button on there that allows you to see the slides in a larger window. And this webcast will be available in an on-demand version somewhere 24 hours, 48 hours after we sign off. So if you miss something, you want to go back and review or send it off to a friend or a colleague, you'll be able to do that. Okay, I think that is enough from me. I'm going to hand it off to John now. John, take it away.
Well, thanks, Rich. We'll get started here on machine vision technology and some of the challenges and selection criteria for image sensors in this space. So first, just let me make some statements here that machine vision is really foundational for machine learning and for artificial intelligence. The sensors themselves are the source of all the data. It's a quite immense amount of data. That is the input to the basic machine vision algorithms. And as we move up on progress or value creation here on this triangle slide, we can see that the next level up is machine learning, where we're starting to train algorithms and understand decision making, what might be considered a good decision or a bad decision. As that advances further to more sophisticated algorithms, we get into the artificial intelligence and work our way up to a cognitive or a human consciousness. Most of our machine vision and algorithms used today fall into the three lower categories for 2019, and we'll explore this further here on the rest of the presentation. There are so many applications that are growing and emerging due to machine vision and artificial intelligence. They fall into three major categories: automotive space for both ADAS and autonomous driving, traffic and ITS monitoring. We have the robotics area for manufacturing, scientific, failure analysis, and of course the retail side that includes logistics, smart home, security. And we'll go into lots of detail on these as we progress through these slides. All of this machine vision and machine learning has been enabled by the growth and the change in our processor capabilities. We started out with very flexible CPUs on the left side of this slide, and That's been really good for algorithm development, but not quite the computational capability that we've needed. Recently, we brought in GPUs, and GPUs are a nice combination of high computational capability and still have flexibility. If we need even more computational capability, we move into the FPGA or the custom ASIC space. But of course, the turnaround time for something like an ASIC can be quite long, and it's difficult to develop these new algorithms. Today, this GPU space really makes a nice compromise between programmability and power. This has enabled in the last 5 years just an immense amount of machine learning and artificial intelligent algorithms. And of course, in most of these applications, the source data for this is the image sensor. Besides these central computing platforms, we also see a big rise in machine vision and edge computing. And edge computing being that machine vision or machine learning or artificial intelligence at the sensor near the source of data collection. And what are some of the reasons for this? Well, number one, when latency is extremely important to the system, having that processing capability next to the sensor can create zero or very low latency. Now, reliability can be a key decision maker for this. When you can't trust that centralized computer or that centralized CPU, you need to keep it local and protected. Bandwidth can be an issue. Image sensors can be 10 million pixels, 20 million pixels, 40 million pixels, and that update rate can be 30, 60, 90, even thousands of frames per second. When each individual pixel is 8, 10, or 12 bits of data, that is a very large amount of information. And in many cases, that bandwidth can be reduced or controlled by having processing at the edge next to the sensor. And of course, when privacy is important for that data, we can process it locally and take attributes from that data and send it to the rest of the system. And in many cases, there are so many sensors in a system, multiplying 10, 20, 30, 40 sensors together would be just too much data for a central processor. So then it can be scaled with local processors. So this is a nice variation on the traditional architecture for setting up machine vision. And we see many of our customers looking for both the edge computing and the traditional methods. The machine vision market is growing quite well. We have about 8% yearly growth that we see. This chart is showing units of machine vision systems. We see some of the largest sources of this growth would be the retail space and logistics. Retail being people tracking, being scanners and things of that nature, and logistics also covering some scanning and factory automation. The growth is continuing and quite strong. It's been solid for the last couple of years, and we expect this to grow quite linearly all the way through 2023. There are many different new applications forming for machine vision, from the commercial side to the industrial side, and there are needs for many types of algorithms and many types of image sensors. So now I'm going to get into some of the detailed applications. We'll talk about some of the needs for the image sensors. Here are 6 examples of some unique applications of machine vision that you may or may not know about. In the upper left here, we'll start with a home delivery system, and this is something that Amazon released some information on just in the near past here. This is a small robotic device, if you will, a miniature car or a drone, and this is released in a neighborhood, and this autonomously goes around the neighborhood, finds the address, notifies the owner that the device has arrived, and opens the door and allows the owner to come out and remove the package. This allows, for example, one large delivery truck to pull into a neighborhood and release, for example, 6 of these autonomous vehicles to go out to the neighborhood, deliver the packages, and then come back. It's an interesting application for machine vision. We have full autonomy here, but we have autonomy on a sidewalk at a low speed rate. So it's a nice transitional phase for launching these types of devices into the market. In the upper center here, we have an example of a drone or object avoidance. And here we have image sensors, global shutter image sensors running at a very high frame rate, looking for possible obstructions or devices in the path of the drone. And this can be very useful for a drone that's not fully controlled by the user, but directionally controlled by the user. Move forward 10 feet, move forward 100 feet, don't hit the telephone pole. And of course, the advancements in the image sensor and the CPU now allow a device like that on its own to move around a stationary object. 3D mapping, upper right, extremely important. We see many different types of applications for this and many different types of technology for implementing 3D mapping. This is an example of a manufacturing device determining what size of packages are coming down the line and what to do in decisions and what type of final box selections would be needed for packing these. Bottom left, warehouse automation or fulfillment. We're seeing lots of companies starting to build these types of devices. This is a case, for example, let's say an Amazon fulfillment center where we have tens of thousands of different SKUs. We need to fill tens of thousands of different orders. How do we get each of these devices, each of these products into the final box? In this case, this is an autonomous robot that lifts up that particular section of shelving, delivers it to a person who could then pull out the proper devices. When it's completed, then the robot moves the inventory back to its original location. So a nice combination of human intervention and robotic devices. Bottom center, this is an example that needs a very high performance image sensor. In this case, is showing a phone display inspection or a flat panel display inspection. Determine if every one of the pixels in the assembly process are working as expected on this display. So in this case, we need a sensor of extremely good linearity and performance, something better than the display, so that it can determine if every pixel in the display is working as intended and the manufacturer is creating a quality product. Sensors for this type of application need to be very fast, very high resolution, very good dynamic range. And in the bottom right, another interesting application, a store that needs to track all the inventory instead of having many people manually walking the shelves and determining what is on the shelf and where. This is an example of the device that can autonomously drive up and down the aisles, scan every device on both sides of the aisles, and determine the current inventory for the store. Another example I wanted to take further into detail. So this is something called Amazon Go, and this is an example of a retail application where a checkout is no longer required. In this case, the person walks in, picks up a device, and walks out, and with cameras in and around the store, it can do the normal checkout and tracking process. So how does all this work? Well, there are a lot of cameras. In this case, there are hundreds and hundreds of cameras up in the ceiling of the store. What's unique and what's special about those cameras? And this is really critical here when it comes to designing systems like this. In this case, the cameras need to be a small form factor. There are so many up in the ceiling. There's limited space. Because they're high in the ceiling and they need to see good resolution, they have to be high resolution for that spatial determination of barcodes of the device. They have to have very good dynamic range. That means the sensor needs to be able to see the dark portions of the scene and the very bright portions of the scene and not saturate. The sensors need to have good SNR or good signal-to-noise ratio when the device is in low lighting. The sensor needs to be able to detect it and have good resolution and good signal-to-noise ratio so it can determine what type of device it is. And as common for many machine vision algorithms, the sensor needs to have a high frame rate so that relative motion from scene to scene can be tracked smoothly. Some additional examples as we move into the not as much consumer but more the industrial space. Many different applications for our larger format sensors. Agriculture, a big growing area for machine vision. This includes machine guidance for devices that go up and down rows of agriculture type of applications, milking, and hyperspectral. Hyperspectral, very important. As an example, a drone can fly over a field and using different wavelengths determine the status of the crops, watering level, UV, and things of that nature. Bottom left, ITS, or Intelligent Transportation Systems. This has seen very large growth in use of image sensors in the last 5 years. And a couple major applications for this, toll roads no longer requiring an RFID or some type of device in the car. The image sensors are now fast enough and of high enough resolution and high enough quality that they can capture the license plate and immediately determine and apply the appropriate tolls. And we're seeing mass adoption for this type of usage for tolling around the world right now. On the right, some more unique applications. In the bottom here, we have an alignment system based off of image sensors. So instead of the traditional mechanical attachment to wheels on an automobile, the user can drive the car up to this device and using machine vision and image sensors, you can determine the different angles of the tires and then determine what adjustments are needed. Lane sorting and belt sorting is shown in the upper right of this, common applications and determination of good or bad in a manufacturing assembly line. And here's some additional examples of that. In this case, a high-speed inspection or sorting system. We need to determine, is it a good apple, is it a bad apple? Or is it, are boxes assembled or are containers assembled correctly? So what are we looking for in a sensor for this type of application? Well, number one, typically this image sensor needs to be global shutter, and global shutter being the electronic equivalent of a traditional DSLR camera where the sensor captures the image for a short amount of time and then turns itself off. We need to have very high frame rates. These devices or these apples are moving by the image sensor at a high velocity, and it's important to capture quickly so that there's no skewing or shifting in the image. We need to have high sensitivity because things are moving by the image sensor so quickly. The capture time must be very short. That means very small amount of light or a small number of photons are entering into the image sensor. So the image sensor and the camera itself has to be high sensitivity. Also keep in mind that these high resolution images at high rates have an immense amount of data. So it's really important that the sensor and the system can transfer data at a high rate. Some of the ways to reduce or mitigate this high data transfer is to focus on ROI or region of interest. And many of our machine vision algorithms today, instead of transferring the whole entire image into the processor, will pick an area of interest and send just that data. Okay, so on Semiconductor, we offer a lot of different types of image sensors to address your machine vision needs. This is just a quick summary of some of the image sensors available. On the left, we have very high-speed, large format image sensors targeted at industrial space. And this is our Python family from 25 megapixel at the top for the 25K sensor down to 5 million pixels or 1.3 million pixels or 480 IE VGA resolution. We also offer CCD image sensors when you have very demanding high linearity and high dynamic range. For your machine vision and ITS applications, we have our new XGS family of image sensors. These are typically about 1-inch optical format global shutter at 3.2 micron, and we have in production today 12 megapixel, 12 million pixels, 9.4 and 8. For your smaller applications, we refer to that as Edge AI, your smaller optical format. We offer 3 image sensors of global shutter type, our 2 meg and our 1 megapixel third inch and our 1 megapixel quarter inch, the AR0144. We also offer many rolling shutter sensors that have very high sensitivity, including our 5 megapixel 521 and our 4 megapixel 430 family. This is just a small example of the many sensors available from ON Semiconductor. On the right, a new sensor, the ARX3A0, and this is an extremely small pseudo-global shutter sensor. And this is targeted for, as we like to call it, machine vision everywhere. When you have a small device or any device that needs to have just a basic sensor determining proximity and things of that nature, something like the ARX3A0 may be a good fit for your application. So for machine vision and AI, there are examples everywhere. We continue to see new applications. We're going to see many more applications. On this slide, just some of the many applications that we're seeing coming out of Asia. Many types of robots for your friend, robots for the factory, robots to make a drink, robots to serve you lunch, and many different variations of retail. Retail for kiosk machines, paying your tickets, sending you a ticket, logistics, even automated parking. And we expect there to be many future applications that no one has thought of yet. It's really an exciting time for machine vision and artificial intelligence. So let me shift gears here and talk about some of the machine vision uses in automotive. So in a typical autonomous driving vehicle or a level 3 type of ADAS device, we'll see upwards of 20 types of sensors in the device. It can be over 10 or 15 image sensors, radar sensors, LiDAR, and even ultrasound. All these sensors have different applications, different capabilities, and they're used together, these different types of modalities, to then operate and offer an ADAS, an AD, or a driver monitor function. So looking in detail of two of the most common automotive machine vision applications, the first one would be ADAS, or autonomous driving. Image sensors for those type of applications, we typically need to have very high dynamic range, bright and dark portions of the scene. We need to have a high-speed capture for moving vehicles and moving scenes that the automobile sees. We need to have very good low-light performance. And, of course, these image sensors need to be automotive grade. Another classification, another use for these automotive sensors is in-cabin for driver monitor systems. And these are devices that are looking back at the driver and determining the driver's state. These types of applications require an image sensor that has a global shutter. It has very good near IR performance just outside the visible range, and that QE, or that quantum efficiency, must be high. And what that means is we need to have a good ability to convert the light, the photons, into a signal for the image sensor. And of course, Again, being in an automobile, they need to be automotive grade. So looking in detail further, these challenges in automotive imaging are quite diverse. The high dynamic range, some examples, pulling out of a parking structure. It could be very dark, and we have the outdoor scene, and we can expect a scene like that to be 120, 130, even 140 dB of dynamic range. And just to give you a baseline, a traditional sensor that does not have high dynamic range capability will typically have 60 to 65 dB of dynamic range. Specialized automotive sensors with specialized pixels and processing can increase its dynamic range to as high as 140 dB. Other scenes that will create high dynamic range, of course, sun, sunrise, sunset, and snowy conditions when there's a lot of glare and reflection. These image sensors for automotive also need excellent low-light performance. In this example, a pedestrian at 30 meters away at night will have a very small spatial resolution, very far away, and in very low lux levels. So the sensor needs to see down to 1/2 quarter lux and have reasonable SNR, signal to noise ratio, so that scene, that image can go into the machine vision algorithm and correctly detect that there's a person. Other key requirements for automotive image sensors are their ability to correctly sense the LED lights and street signs. One of the issues with the LED street signs, LED parking lights, and everything based off of LED is it is actually pulsing on and off at an unknown frequency. Traditional image sensors, when they try to capture that, there will be a beat pattern between the refresh rate of the LED and the capture rate of the image sensor. And typically we'll see some type of missing portion of the scene. So high performance automotive sensors with LED flicker mitigation can correctly capture the image. The in-cabin application, here's a more detailed look, is actually required to capture an image of the driver under many different scene conditions. We will need to capture the driver at night when it's dark. We need to capture the driver during daytime, or if light is shining in from, for example, the driver's side window. And this algorithm must be quick and, again, very robust to these scene conditions. So implementation of this requires a global shutter sensor, with an active light source that cannot be seen by the human eye. Thus, it's at the near IR frequencies above 900 nanometers or 950 nanometers. That's a frequency that can be very difficult for image sensors to capture at. So we need a global shutter, good QE, i.e. good sensitivity at this 950 nanometer. All this combined in a small package so that the customer or the driver does not see cameras in front of them all over the dash. For these type of applications, we offer our high performance AR0135 and AR0144 global shutter image sensor. There are many different applications for in-cabin. Just wanted to share with you a couple. There's the traditional driver monitor, where the image sensor and that algorithm needs to determine the status of the state of the driver. Are they paying attention? Are they on their phone? These image sensors for driver monitor can be used for airbag adjustment, for driver identification, and for authentication. New and emerging applications in the automotive space is occupancy monitor, moving beyond just the driver. And common types of applications for this can be reminder and detection of a child in the back seat, reminder detection of objects, and also video recording, for example, in a taxi type of use application. and even detection that your pet is in the backseat. ON Semiconductor is a market leader in automotive space. And we offer the largest family of products for your automotive applications. And we classify these into viewing and sensing, ADAS and autonomous driving, global shutter for in-cabin, edge for the sensor processing unit, and our radar and LiDAR family. For each of these spaces, we have the most number of products and the highest performance in the industry right now. If you have a need for automotive products, we look forward to discussing with you. So a little bit more detail into some of our products to help you with your machine vision solutions. So ON Semiconductor, we've actually been developing and designing image sensors for quite some time. The intelligent sensing group of ON Semiconductor is actually a combination of many different image sensor companies, which you have likely heard of over the years. We started with Kodak in 1975 with some of the original Bayer pattern applications. Kodak became TrueSense and acquired by ON Semiconductor. Another path has been JPL to Photobit to Micron to Aptina and then ON Semiconductor. We also have radar and LiDAR from IBM and Sensel. And the last path, the Phil Factory and Cypher Semiconductor. So lots of different heritage, lots of experience here, and many years of design and development of image sensors. The first product I'd like to talk to you about is our AR0144, and this is a small optical format, i.e. a very small sensor of resolution of 1280 by 800, about 1 million pixels or 1 megapixel. And this has a 3-micron pixel. This device will operate capture frames at a rate up to 60 frames per second. So this global shutter is really key for enabling image sensor. And I'm showing two images on the right here. This is a spinning disc with some barcodes placed on it and moving around at quite a high angular velocity. On the left, we have the capture from a global shutter device, and on the right, we have the capture from a traditional rolling shutter image sensor, the type of image sensor that you would find in your mobile phone. A traditional sensor, the way it captures will distort the image, and we can see on the right it's very difficult for a machine vision algorithm to then determine the results of that barcode. The global shutter on the left keeps the image square without distortion. So global shutters can be very useful for any type of scene in machine vision that has high motion. Other key things to look at in your global shutter device is the shutter efficiency. The shutter efficiency is the sensor's ability to block light when it's not capturing. These are electronic devices. You can imagine this to an old-fashioned camera. When the shutter is closed, there's some type of metal blocking the film. No light is going into the film. The shutter efficiency is the validation or the specification for how well light is blocked when not capturing. When you are capturing, it's very important that the image sensor has good sensitivity, good ability to capture light, and good ability to capture light at many different frequencies. So much of the machine vision algorithms are not about capturing a visible image. They're about capturing an image to do some type of processing. In many cases, we operate just outside the visual spectrum near IR. So it is important to look at your image sensor's QE, quantum efficiency, or sensitivity at near IR frequencies. The 144 offers a very small format, about 4 millimeters diagonal, and as mentioned before, up to 60 frames per second operation. Here's some examples of the image sensor's low light capability. Here we are at 22 lux at a 6.5 millisecond integration time, and we can see a zoom in of the capture on the right and showing very good signal to noise ratio, very good ability for a follow-on machine vision algorithm to correctly calculate and process. Next, I'll talk about our XGS family of products, and this is our large format, high-speed 3.2 micron global shutter family. So the XGS image sensor family is very high bandwidth. At 3.1 and global shutter, it offers high performance and extreme low noise. And we offer this device today in 3 resolutions, 8 megapixel, 9.4, and 12 megapixel resolution. And this can be used for ITS, for broadcast, and for general purpose industrial machine vision. The 3.2 micron gives very good resolution and very good sensitivity. This advanced pixel type gives us exceptional signal to noise ratio, some of the best signal to noise ratio in the market today. And of course, the global shutter, another example on the right, allows one to capture high motion devices without distortion. We offer a family of these products. Our Python generation at 4.8 and 4.5 microns, offering exceptional high speed and sensitivity. And the newest XGS reduces the pixel size and allows you to have increased resolution for the same optical formats. So if you have a limitation of space, for example, largest possible sensor may be 1 inch diagonal. With our Python family, you could go up to around 5 megapixel. With the XGS, we can increase that up to 12 megapixel for that same X, Y, and Z dimension requirements. The XGS family of sensors, 3 resolutions available today. We offer this in color and mono SKUs, and we also have multiple speed grades depending on your application's needs for higher capture rates with more output and more power and more cost, or more size-friendly devices at lower frame rates. Many options for you, the customer, to decide what's appropriate for your application. Here's some detailed specifications on the XGS family. Note the global shutter efficiency, a ratio of 4,000 to 1, very good linear full well, a proxy for that dynamic range at over 10K electrons, and up to 68 dB for this global shutter device. And this is a 12-bit ADC giving very good resolution for luminance levels. Also in our large format sensors for machine vision, we have our Python family, and those are offered at 4.8 and 4.5 micron pixel size. We offer this in 9 products and 4 different package sizes, very flexible, that you have multiple resolutions for the same family of device. And the Python will operate up to 815 frames per second, or resolutions as high as 25 million pixels. Here's a table showing the complete family of Python devices from the SVGA resolution on the left, 800 by 600 for our Python 480, all the way up to the largest Python family image sensor at 5120 by 5120 square optical format for 25 million pixels of resolution. We also offer design support to help you. We have our DevWare software and a whole family of adapter boards and interface boards so that you can quickly bring up your image sensors, validate them, and design them into your systems. This award-winning software includes full diagnostics of the captured image and the ability to adjust all the sensings, all the settings inside the sensor. So in summary, the advancements in AI and machine vision continue to expand, and we see many new applications emerging, and we expect to see many new that we have yet to think of. There are unique challenges for the image sensors. At ON Semiconductor, we have a whole family of image sensors for machine vision for the many different applications and needs, and we look forward to supporting you in the future. Thank you for your time today.
Awesome, John. Thank you very much. That was very interesting. I love the examples that you threw out there. I happened to be in one of those Go stores just the other day, and it's pretty cool how that thing works. You walk in, you walk out, and next thing you know, you got a charge in your credit card. It was very impressive. Okay. As I said, we have some time to answer people's questions, and we have a bunch. Ask away. Anybody out in the audience, feel free to type your questions into the console, and we'll ask as many as we can. Okay, John, hopefully you had a drink of water, and we'll get to the first one. Here's an easy one for you. Which of ON Semiconductor image sensors are recommended for road traffic monitoring? And I'll throw in there, why? Why are you recommending that one or that series?
Okay. Well, that's a good question. So traditionally, the recommendation has been CCD devices, and we do offer a whole family of CCD devices, but more recently that market moved to CMOS sensors, and our latest family, the XGS family, has the highest performance in terms of dynamic range and low light SNR. So that is our recommendation, the XGS family. And today we offer that up to 12 megapixel, and we will continue to grow that family to offer even higher resolutions here throughout the rest of 2019.
How high can you go, and how high is high enough, and how high is too high?
That's a good question. Typically, our customers or the application has a limit on the size of the camera itself. So that will drive the optical format.
A physical limitation you're referring to?
Absolutely, a physical limitation.
Okay.
Because we can make the sensors larger. And larger sensors then require larger optics and a larger lens, which then have to have an increased distance away from the sensor. How many times have you seen a professional camera person at the side of a football game, and he has a giant camera with a lens that sticks out 2 feet? Well, that's a very expensive lens and limited use cases, and not something that, for example, we're going to put on every ITS camera for the original question. So optical format or physical limitations typically drive the upper bound, and then it's up to us image sensor manufacturers to give the highest sensitivity, the highest resolution within those boundary conditions. And the XGS, as I mentioned before, reduces the pixel size from 4.5 down to 3.2, so that gives increased resolution for that same optical format.
Very good. And that guy at the football game is always one who gets knocked over by one of the guys running out of bounds. Let's see. Specific to machine learning, what are the limits of machine learning? And two-part question, what fail-safes will be needed for automobiles in this space?
Well, limits. So many of us in the tech industry know to not put any boundary on limits. So we're going to be limitless in terms of the capabilities of machine learning. But keep in mind, with the first slide that I showed, that triangle there, machine learning is foundational going into artificial intelligence and moving up into a cognitive space. So we will see many layers progress over time as the CPUs or the processors increase in capability and the industry creates more complex algorithms. As far as fail-safes go, especially for autonomous driving, there's a lot of discussion about that in the news today, and that kind of brings in the question, when will autonomous driving really be available? We see multiple levels of autonomous driving, level 1, level 2, level 2 plus 3. It's going to take time until we reach full autonomous driving at level 5. And the market and the industry is just going to slowly work their way up from the current ADAS driver assist up to full autonomous driving.
But that has nothing to do with the vision element, right? That part is already there.
That's correct. The vision element is there, and we offer many types of sensors, and of course we're constantly improving the vision capabilities. The more complex and the more difficult part for autonomous driving are those algorithms themselves, being fully validated, sufficient road testing miles, and government and other types of the certifications and safety validation.
Should we expect to see more integration into those sensors? I mean, will they continue to be discrete, or do you see the day where they're loaded with memory and a processor, all maybe not within the same piece of silicon, but within a multi-chip module?
We do have some examples where the level of integration increases, and it depends on the application. For our highest performance industrial image sensors that are at the bleeding edge of the technology, those will stay as discrete devices. It's very difficult, extremely difficult to make good performance image sensors. For some of our smaller resolutions, then we can integrate some of the edge processing or the image sensor processor with the light collecting the image sensor. And that is some of the trends. For example, surround view or backup cameras for automobile applications. In many cases, there'll be an integrated solution.
Okay. Somebody just asked a variation of the question that I just asked, and with a little more detail. Do ON Semi's NIR cameras perform any pre-processing of the captured images, which I think you mostly answered, but then if so, would one have access to the raw data before the pre-processing, or details of the pre-processing available to the user?
Yeah, that's a good question. Yes and yes. For the applications that use, for example, an edge processing of some type or some analytics, we also offer bypass modes so that downstream processing can have access to the untouched original source data. If it was a color image, that would be that buyer RGB data or black and white mono data. And, of course, any process results data also available. So, yes, we found that it's extremely important to have the process and unprocessed data available.
Okay. Sticking to automotive, I'm not even sure if this question is for you or not, but how do automotive image sensors detect moving pedestrians as opposed to static objects?
Well, ON Semiconductor focused on the image sensor. Yes, agree that's a little bit more for the algorithm, but how is that detected? Well, it's a series of still captures. So we offer very high frame rates. 60 frames per second is common for the automotive ADAS and AD space. So then a series of still images goes into the core processor, the autonomous driving processor, and it then, studying those series of images, will determine if that, for example, that pedestrian is stationary, moving in the path, outside the path. And that's just...
And is I'm sorry, go ahead.
No, go ahead.
No, go ahead.
I was just saying
I was going to ask... After you. Okay. I was going to ask if the solution to that problem, I don't know if problem's the right word, but issue is just putting more and more images in front of the compute. And I mean more and more, I mean like running thousands and thousands and thousands of images. So there's never any discrepancy over what is a real person and what is not a real person. Is that the solution, or is it more about artificial intelligence doing interpretation?
It's more about the latter. The algorithms, we can call it artificial intelligence, that machine learning, that's core IP and technology as part of that processor for that given application.
Okay. And where does that responsibility lie?
Well, these are complex problems, and it's a large ecosystem of suppliers to offer different pieces. As we discussed today, ON Semiconductor has a wide range of image sensors, which is the first step of collecting that real-world data and bringing that into your machine vision or machine learning algorithm. We also offer edge processing when you want to do some of those analytics near the sensor, and we partner with all the leaders in the automotive and other machine vision space to offer to our common customers a complete system solution.
Okay, very good. But at the end of the day, I guess the ultimate responsibility lies with the automaker, right? I mean, the buck would stop there, I would guess.
Well, of course, they're the final manufacturer of the device to the end customer, so yes.
Okay. All right. Switching gears, this one. Will drones completely replace humans in warehouses in the near future?
Well, that's interesting. Hopefully we're not implementing the Terminator scenario here. Drones are one space, but robotics or autonomous vehicles might be, a better name for all that. And I showed some of the fulfillment examples. I don't think replaces what will happen, but side by side and absolutely utilize. We will see many more autonomous devices, call them drones or robots, but it's in parallel or conjunction with the human. As I've seen it today, the use case for that fulfillment is some type of autonomous device to bring all the material to a central location for the final packing of a box to ship out. So we don't see it as full replacement, but it leaves the more exciting jobs to the human.
Yeah, and I think where this really hits home is the places you don't want to send a human into a burning building and, those types of scenarios.
Absolutely.
Okay. Let's see. How do you acquire a USB-based demo kit for home robot vision project?
Great question. So you can go to onsemi.com, or you can contact your local representative for ON Semiconductor, and we can help you with that.
Okay, that was an easy one. Here's one that we've touched on mostly. When do you expect to achieve 100% safe autonomous driving imaging in all situations? And also, if you know the winning numbers of the lottery, let me know that as well.
Well, isn't that the $1 million question? Both of those, actually.
Yeah.
It's tough to say. I'd estimate about 5 years. I think the technology will be here sooner, but legislation and that absolute 0.0001 use case, that's going to take some time until we're all comfortable with it. We're definitely going to see a lot more use of level 2 plus and level 3 applications where the driver is still required to monitor the situation or the autonomous driving can be used in selective good scene conditions, good road conditions. It's a journey, and it's going to take some time to reach full autonomous level 5.
What's really the most difficult part of that? What's the piece that people are struggling with, or is the hardest?
Well, it's a complex problem, and we have a lot of different one in a million use cases that need to be worked out, need to be thought through, need to be validated. And the public has zero tolerance for a machine to make an error. And we can all think of very unique conditions where it's difficult to decide what's the correct answer. All those types of things mean it's going to take some time until we sort this out. But it's amazing the level that the technology has achieved today. And we have lots of interim applications till we reach full autonomy. I showed some today that are, autonomous delivery devices and things of that nature. It's an exciting time, and the whole industry is making great progress towards full autonomy.
Yeah, you bring up a good point, and it's probably not a discussion we can answer in a couple of minutes, but people have accidents all the time. And when there's one autonomous vehicle accident, it's the biggest news to hit, ever. And that drives me crazy. But, anyway, any comments on that?
No, I agree. I mean, we're happy at the amount of lives that we've saved so far with all the safety devices that the industry has placed into automobiles, the backup cameras, the surround view, the collision avoidance. We've really made great headway, and I'm personally very excited to watch the industry continue in this direction.
That's probably the answer to the unasked question that I just posed, that there's not enough PR around the good stuff that happens. There's only, what's the phrase? Good news travels fast, bad news travels faster. Anyway. Yeah. Are you guys going to be at any upcoming trade shows where people can actually see a live demo of this stuff?
We're always at many of the industry trade shows. We typically list those at onsemi.com, and we look forward to demonstrating these for our audience. Okay.
Very good. I think we are wrapping up here. That's about all we have time for. So I'd like to thank John for making a really great presentation, bringing some really important issues to light, and most importantly, giving some solutions to those issues. I know I very much enjoyed it. I'd like to thank ON Semiconductor for sponsoring this event. And of course, we are not able to do any of these types of events without you, the engineer. As a final reminder, all Open Systems Media webcasts are copyrighted and may not be recorded without prior permission. Thank you all for attending, and have a great day.